So everybody brought in cookies.
Okay, I think we're recording now. So welcome back, everybody. I think on Canvas this morning, as I was publishing, I do have a link. I don't know if I'll keep it up there, but there's another link to a video that Mrs. Napholtz made a couple years back when she was out. So I'll put both of them up there. I guess it doesn't really matter. We teach the same thing, same way. All right, so section 7.5, exponential and logarithmic equations and inequalities. So what we're going to do with the second part of chapter 7 is talk about what other things that we could do with them. Like the first thing, in section 7.5, we're going to solve equations and inequalities. In section 7.6, we're going to talk about a different base of logarithms, log base e. We're going to talk about in section 7.7 and 7.8, we're going to talk about how do we transform logarithmic functions, just like we do in every chapter, transformations. And then in section, I think it's 7.8 maybe, we talk about how we do regressions with logarithms. Because really, logarithms and exponential functions are ones that occur naturally a lot. Yeah? Things increase at an exponential rate or decrease at an exponential rate in nature a lot. So what we're going to do with those is, or what we're going to do in that section is just the same thing that we've been doing before. You know, putting it on our list and seeing what happens and making an equation off of that. Now, that being said, the next assessment is our Chapter 7 test. Okay, the next assessment is our Chapter 7 test. So we got a while till then. It actually ends up falling on. No, it's like the late start day in March. Yeah. So because March isn't too far away. It's only 9 days away, right? Yeah. I think it's like March 3rd or something like that. But it's a 2-day test.
So what?
It's a 2-day test. Wait,
That sounds scary.
well, it's not really a 2-day test. It's like a 1.5-day test. So it actually ends up being okay that it falls on one of those late start days, because then I can give you the no calculator part on like the half-day part. And then you'll get your full day for the calculator. So it actually works out really good for us. We were like, oh, happy accident. Okay, so, but the next assessment is not going to be until until March, right? So we got a while till then, so we can kind of hunker down and get settled in. Stop distracting me. All right. Okay, so exponential equations. People always freak out when we get to exponential equations.
Oh.
And I don't know why. What?
Yeah.
Okay. I was going to say, do you want to go in the hall?
No, I just did.
Okay, I should write you.
Thank you.
Ooh, I should write you a pass to class, and I should take attendance.
Welcome to TED Talk with YouTube today. What should we talk about? Spinach? So you know that Popeye guy from that old animation? Eats spinach.
We're going right up to the microphone.
Remember, all of your conversations are being recorded.
Exactly.
March 4th? Until everybody just until when somebody throughout the video.
Oh, I think this is a little
It's gonna put throughout the video. Like some thing. Oh, I
I
have to
think
subscribe
it's
now.
27.
Gotta use the algorithm.
27 is Friday now, so don't tell that weekend.
Begging section. Don't forget to hit that notification
This
bell.
video is sponsored by.
Okay, and we're back. Sorry about that.
Cut all that out.
So talk about your
Yeah, should I?
sponsor.
You talk about spinach and subscribe.
Spinach? Yep.
Yeah, spinach.
Talk about spinach. Popeye.
Yeah.
Yeah, exactly what he said.
Yeah.
All right. So when we talk about solving exponential equations, we are actually also going to talk about solving logarithmic equations today as well. We're going to reserve the inequalities a little bit, I think, for tomorrow, if I'm remembering correctly. But equations, solving exponential equations require, I don't want to say difficult methods. They're just, you have to be able to think outside the box for a lot of them. Okay, you have to be able to like just throw stuff at the wall and see what sticks. Okay, because the same method is not going to work every time. Okay, Like when you go to solve a linear equation, you do inverse operations and you just solve the variable, right? You know, just like a basic straight up linear equation, solve for x. Boom, done. Then we did quadratics. Okay, does every method of solving the quadratic work? No. Sometimes you got to do completing the square. Sometimes you got to do quadratic formula. Sometimes it does factor. Sometimes there's no b term. You can solve directly. But when we get to exponential equations, it's a little bit more involved. There's a couple different things that you could possibly do. And there'll be times when you're solving an equation and you'll go down the rabbit hole and you'll end up being like, oh, that got me nowhere. So you'll have to erase, go backtrack, and start back over again, okay, using a different method. Okay. And that's what you guys kind of freak out about that. Contrary to popular belief, you like to be told exactly what to do, when to do it, and how to do it. So here's my best take on the different things that you could possibly do to solve the exponential equation. And kind of logarithmic equations. So first method, try writing them so that the bases are the same. If possible, and again, this is like an if possible thing. This method won't work every time. Try writing them so that the bases are all the same. That sometimes works. Might help you out, might simplify things for you. Another thing, take the logarithm of both sides. Take the logarithm of both sides. You'll see what I mean in a second. And then the last method is to rewrite, to change forms, to go from exponential to logarithmic form. That is generally the one that gets forgotten about. That's like a simple one that a lot of people just don't remember to do. If you're stuck and you're like, I can't think of anything else I could possibly do, if it's an exponential form, try to change it to logarithm. If it's a logarithm, try to change it to exponential. All right. Now, obviously, this is a really silly definition. A logarithmic equation is an equation with a logarithm in it. Like your English teachers would freak out about that definition, right? A logarithmic equation is an equation with a logarithm in it, right? That's silly. We can solve logarithmic equations by using the properties of logarithms. Now, why am I putting this up there? Well, because you can't forget about the things that we learned back in section 7.4. We can't forget about addition means multiplication, subtraction means division, power means bring it out front. We have to remember when things cancel. That's going to help us solve a lot as well, right? B to the log base b of x would cancel to be x. Log base b of b to the x, that would cancel, leaving just the x. So you've got to know when things are going to cancel as well. Remember, whenever you have a logarithm within an exponent, it cancels, as long as they have the same base. Whenever you have an exponent within a logarithm, that with the same base, that will cancel as well. They will undo each other like that. Okay. Now, this is kind of funky. Always check your answer. And there's going to be a couple different reasons why you should always check your answer. Always check your answer. And when I say always check your answer, you guys, again, this is another one where you're like, yeah, it's not getting the same thing. If you guys ever have to round it all, right? If you guys ever have to round it all, and then when you go back and you plug your answer in, is your answer going to be exactly correct on both sides? No. Okay? It's going to be close because you had to round, but it's not going to be exactly the same. Okay? So just make it reasonable. Your check should just make it reasonable. Sometimes we will check and you'll put it back in and it's not going to work. And we'll talk about what's going to happen there. That's something funky happened somewhere along the way. But we'll plug something in and it won't work. And we'll have to be like, okay, what went wrong? What happened? But again, let's crawl before we walk here. Okay, so let's solve this. Now, there's going to be, for a lot of these problems, you're going to be able to do it in a variety of different ways as well. Some of the problems, only one method will work. Some problems, all methods might work. There's a way that you could do all methods. What would you guys like to do? What's the first method? What was it on there? Make the bases the same. Oh, I can do this method. What's my base on the left side? 3, right? How do I make 27 out of a base of 3? 3 to the third. Right? This is possible here. If this was anything, say this was 28 on the right side, could I do this? No. 28 is, I can't make out of a base of 3. And guess what? When this happens, guess what we could do? Set the exponents equal. Well, that's nice. That's convenient. So x is 1.5. Okay, now let's check our answer. Did we round to get 1.5? No. So we should get an exact answer when I plug it back in. I'll use my calculator real quick. Get it. Get. All right. So we got 2 to the 2 times 1.5. 3. Oh, duh. 2 to the third. Yeah. That. Wait, oops. 3 to the third. Sorry. 27. Still before you. 3 to the third is 27. That does check out, right? Okay, good. This answer I know is correct. X equals 1.5. That's my answer. Good. Yes.
So when the bases are the same, how are you able to strike them both and have the exponents equal to each other?
That's a great question. Why does that work? Well, if I took the logarithm of both sides, and especially the log base 3. Try to fit that in there. Because I can perform the same operation on either side and it's still equivalent, right? What happens here? What happens here? Right? Leaving a 2x and a 3. So that's why that works. Okay? What else can we do? There's another method that might work. Do you see how it's in exponential form? What if I just straight up changed it into logarithmic form? Log base 3 of 27 is equal to 2x. Right? I'm just changing forms, right? Log base 3 of 27 is equal to 2x. Well, what is log base 3 of 27? 3. 3 is equal to 2x. 1.5 is x. You see that? What's the second method? Take the log of both sides, right? Or no. Take the log of both sides. Yeah, sorry. Take the log of both sides. So if I wanted to do that method, let's see if that method will work. I would take log, yeah, I could do log base 3 again, right? Just like I showed in that example right there. Log base 3 of 3 to the 2x is equal to log base 3 of 27. You just have to strategically pick which base that you want to use with your log. Because what happens with log base 3 of 3 to the 2x? Cancel the 2x. What is log base 3 of 27? We just saw that. 3. X is 1.5. So a variety of different ways could work here. All 3 of our methods works. Could I possibly make the bases the same here? I mean, there might be some weird fancy math that I could possibly do, but I don't think so. Roman numerals? So maybe I should switch it up. Now, does everybody understand why I'm saying I can't make the bases the same? I can't make, like, I could switch the base into 2 here, couldn't I? Like, couldn't I switch the base into 2 to my 4? But can I make 5 out of a base of 2? Like, 2 to the what power is going to equal 5? No, that does not work, right? So I can't make the bases the same. I can't make this out of a base of 4 either. Like 4 to the what power would be 5? No. So I've got to do something else. Maybe this is an exponential form. Maybe we should rewrite it into log form. Right? Let's try that. Log base 4 of 5 is equal to x minus 1. Does that help us? Now, you have your calculators for this. does that help us? Can you calculate log base 4 of 5? So do it. I have to do the change in base formula, but you guys can do your fancy log base function. Log 5 divided by log 4 gives me 1.16. You can't forget that you can evaluate a logarithm. When it's log base any number of any number, you can evaluate that. You can actually plug it in your calculator and get a decimal. Okay? I wonder if I could take the log of both sides. Well, I could, yeah, I could. I could take log base 4 of x to the x minus 1 is equal to log base 4 of 5. And then it ends up being the same thing. Log base 4 of 4 would cancel to get the x minus 1. Log base 4 of 5 would be rewritten just like this. So it ends up being the second step that we had here. Okay, let's try the next one. Oh, I should check. Oops, I should check. Now, did I round for this answer? So watch what's going to happen. I take 4 to the 2.16 minus 1. I should put that in parentheses. 4 to the parenthesis 2.16 minus 1 is equal to 5. So is that equal to 5? Close enough, right? Close enough. Okay. Take a look at this one here. Okay, I'm going to make the bases the same. Now, can I make 8 with a base of 4? 4 to the what power is 8? If you said yes, 4 to the what power is 8? He says with a smile. 1.5. Yeah, be right now.
Yeah, it's 8.
Now, so we cannot make 8 using a base of 4. Can't do it. Okay. So let's use 2. Can't I reduce 4? 2 to the what power is 4? Second, right? I'm just transferring this into 2 to the second. I'm just going to transfer this into what? 2 to the third. I'm just rewriting these with the same base. Okay, what do I do with the powers to the powers? Like, what do I do with this 2 and the 3x minus 1? Not yet. Yeah, multiply. 2 to the 6x minus 2 is equal 2 to the 3x plus 3. Right? Because power to a power means you multiply, right? Now I have the same base on left and right side. I can set equal now. 6x minus 2 is equal to 3x plus 3. Subtract the 3x, add the 2, x is equal to 5/3. Does that make sense? I could take the log of both sides. I could try to turn it in from logarithmic to exponential. I wouldn't. This is the easiest way to do that. Okay. Shall we try another? I didn't check my answer there.
That's right.
You checked it, thanks. Check. Okay, I've got log base 6 of 2x minus 1 is equal to negative 1. Log base 6 of 2x minus 1 is equal to negative 1. Okay, so what am I going to do here? Well, can I make the bases the same? No, that doesn't make sense, right? I'm talking about exponential base. Yeah, no, that doesn't make sense. Could I take the log of both sides? Log within a log. Ooh, no, thank you. But This is in logarithmic form, right? So let's just change it into exponential and see what happens. 6 to the negative 1 is equal to 2x minus 1. Oh, man, that's not bad at all. What is 6 to the negative 1 power? 1/6. 1/6 is equal to 2x minus 1. 1 and 1/6, I'll put it into a decimal now. 1 plus 1/6. 1.16 repeating, 1.17 if we will. Because we're going to have to divide by 2 anyway. Divide by 2, 0.58. I took 1.17. What would that be? 0.59. Okay, whatever. Yeah, we get it. Yeah. Yes.
How did the negative 1 do so?
I added it.
Oh, I'm not looking at that.
This?
Yeah.
6 to the negative 1 is equal to 2x minus 1. That make sense? Questions about that? Now, what will happen if I plug this back in? Let's just double check it. Log base 6 of 2x minus 1. Well, 2 times 0.58 minus 1 is going to get me this, like 0.16, right? So I need to calculate log base 6 of 0.16. Log base 6 of 0.16. You can do that in your calculators really easy. I cannot. I have to do log of 0.16 divided by log of 6. Is it close enough to negative 1? Yeah. Close enough for me. Yeah.
Is it okay to keep it in fraction form rather?
Totally fine.
Okay.
Yeah. That would make it right on.
Yeah, 7/12.
Yep. Okay, log of 3x plus 1 minus log of 4. Okay, so what does the subtraction in between the logs tell us to do? Division. Okay, so simplify as much as you can using your properties of logarithms, and then start throwing stuff at the wall. Log of 3x plus 1 all divided by 4 is equal to 2. Okay, I see it's in log form. Let's do the same thing we did last time. Let's try to turn it into exponential. What's the base of my log? 10. 10 to the second is equal to 3x plus 1 all over 4. And now this becomes an equation that I can solve pretty easily. This is 100 is equal to 3x plus 1 over 4. That gives me 400 is equal to 3x plus 1. That gives me 399 is equal to 3x. So 133 is equal to x. Let's double check that. Let's throw it back in. I can do this because it's log base 10. Sweet. Log of 3 times 133 plus 1, all minus log of 4. Hopefully that comes out to be 2. Perfect. Questions about that? Okay, let's keep it rolling. All right, so caution. Watch out for calculated solutions that are not solutions of the original equation. Yes, there are times when you will get a solution from your equation, and it's not actually going to be a solution. Weird. We'll have this like for the rest of the year. We'll have to watch out for this for the rest of the year. There are methods that we use to solve equations, to solve more complex equations, that make what are called extraneous solutions come up. Okay, solutions that we solve for, but are not actually solutions to the original equation. Okay, I know it's like really weird. Like, what? If we solve for them, they should be solutions. Not exactly. Okay, here's what I mean. There are times when they happen. There are very specific times when they happen. Log base 12 of x plus log base 12 of x plus 1. That's all equal to 1. Okay, so what do we do then? Well, what does the addition in between the logs tell us to do? Multiplication. So this turns into log base 12 of x times x plus 1, and that's all equal to big 1. All right, let's distribute in there. So log base 12, if you want to put parentheses around this, x squared plus x, just to be clear. All right, so this is in log form. Heck, why not? Let's try to put it into exponential. X squared plus x is equal to 12. 12 to the first, obviously, but just 12. Everybody follow me what I did there? 12 to the first is equal to x squared plus x. All right, now, this is a quadratic equation here, right? Let's just solve it like we do any other quadratic. X squared plus x minus 12 is equal to 0. Would we like to complete the square or use the quadratic formula? Nah, we'll just factor. X plus 4, x minus 3. X equals negative 4, x equals 3. Right, which one's wrong? What and why is it wrong? That's the more important question. Which one's wrong and why is it wrong? Can anybody, don't plug anything in your calculator just yet. Which one's going to be wrong? Why do you say negative 4? Because negatives are just weak, right? But it's got to be the negative. It can't just be 3. What would happen if I went to plug in negative 4 into the very first term? Log base 12 of x. Log base 12 of negative 4. What happens in your calculators? Go ahead and plug it in your calculator. Log base 12 of negative 4. Just try that.
It has a stroke.
Oh no.
What's it say? Non-real
Ah,
answer.
yeah.
No, don't worry. We're not going to calculate these. For our purposes here, we're just going to throw out that answer. But why are we throwing out that answer? Because it's non-real. Why is it non-real? Think about the graph of a logarithmic equation. Right? Any logarithmic equation looks like this, right? Where is negative 4? Over here.
Oh no.
Right? Is it defined in our negatives? No. The logarithm, unless it's been like transformed left or right, is never defined within the negatives. So negative 4 is not defined within this log. Okay? What's defined? Anything above 0. Okay? Now, does that mean whenever I get a negative answer, I immediately throw it out? No. That means if I plug it back in and I go to evaluate a log of a negative number, that's when you throw it out. Okay? Like I plug this back in and I'm going to be forced to take log base 12 of negative 4. No, can't do it. Because what if it would have been like when I go back in, maybe it had said, I know it doesn't, but maybe it had said log base 12 of x plus 7. Well, when you go to plug back in negative 4, you get log base 12 of negative 4 plus 7, and then you'd have to take log base 12 of 3, and that would be okay, right? Then you'd be taking the log of a positive number, and that's all right. You just have to go back and try to check it. Now, what would happen if I plugged in log base? Let's try 3. You guys with your log base function, because that's going to be a bear for me to plug in. Do log base 12 of 3 plus log base 12 of 4. Because that's 3 plus 1. Log base 12 of 3 plus log base 12 of 4. What do you get? You get 1. It checks out. So my only possible solution is x equals 3. Now, how did this happen? Why did this happen? It's because we took an x squared. Whenever you take an x squared, extraneous solutions may arise. Now, do they always do? They may arise. It could be one of them that could be no solution. It could be both of them, they end up being no solution. It really kind of depends. You just have to plug it in and see. Okay, try one of these on your own here. Go for it. Mark, it's set.
I forgot how to read.
Oh, that's. Wait, but like, I don't want to do that.
What? No. I don't need one.
Yes, off the rack.
That's not fun. I don't want to do. You get very good by Yes.
Okay, did we all get at least to here? Yeah, well, after we foiled the x minus 1, 3x minus 1. Okay, now here, transform it into exponential. 4 squared is equal to 3x squared minus 4x plus 1. So that's a 16, right? Subtract it over to the other side. Okay, solve that equation. By whatever means necessary.
Yeah.
You just multiply number and you get a number. What is it? Negative 5. Yo.
Okay, so it's one of those ones.
Plus.
This is factorable, by the way.
Oh.
Unless you want to just use the quadratic formula, that's a
I'm doing it. Everything is being done. Why?
Three. Is it always going to be the positive answer that's going to be the right one? Or
not always.
not always?
Not always. It depends on like how it plugs in.
Oh.
Yeah. If there was like a negative x up there, then it would turn positive. So the positive answer would actually be the wrong one. You know what I mean?
Yeah.
So it all depends.
I'm getting wacky stuff. I don't know, but this is right Okay.
Oh, you're looking at that too.
No, I was
What, you're looking at the door?
Okay, so we've got those two answers, right? X equals negative 5/3 and x equals 3. Guys, what happens if you plug in x equals negative 5/3? Does it actually not work? I should check it. Well, think about it. Negative 5/3. If I go to plug in negative 5/3 and I subtract 1, it's only going to get more negative, right? Can't have that. I'd take log base 4 of a negative number. No good. Now, what would happen if I plugged in 3? Is 3 still a positive number when I go to evaluate the log? 3 minus 1 is 2. Perfect. Log base 4 of 2. Plug in 3. So 9 minus 1 is 8. Log base 4 of 8. Yeah, I would be plugging in logs of positive numbers, and that works. So why are we getting extraneous solutions? Because the domain is restricted, right? The domain for the logarithm is restricted. That's why, right? And it all happens really here, from this step to this step, right? Because what did we transform it in? We had it in logarithm form, where the domain was restricted. And then what did we do in that step? Turn it into exponential. Is the domain restricted in exponential? No. What is the domain of any exponential? All real numbers. So that's why I allow myself to find the other one when it's not really there. I turn it into a different thing, which makes other solutions come up. Okay. All right. Well, that's all we got for today. Everybody say bye to YouTube.
Bye.
Subscribe
Don't forget to subscribe
And like.
and like.
and like, I
Comment.
guess.
And comment.